All right, so now let's take a deeper look at some of the strong acids and bases. And we'll take a look, first of all, at the strong acids. And again, these are ones that you would have seen or that we would have seen back in Gen Chem 1. So I'm going to list and highlight this table here. And we're going to say these are names that we need to know. To commit these to memory, there are many acids. Very few of them are strong acids, and you need to know them. Commit these to memory. So both the names and the formulas for these. So the strong acids, when we look at them, and when we defined what strong versus weak was earlier, right? Strong acids dissociate completely. Okay, they ionize completely. All they have are just ions in solution, lots of protons or hydronium ions in solution. So we don't treat them as equilibria. Instead, we think of them as going to completion, which means the arrow that we use here is a normal arrow going from left to right, full-headed arrow going from left to right. So hydrochloric acid, HCl, right, dissociates in water to produce only hydronium ions and chloride. Hydrobromic, same thing, hydronium and bromide, hydroiodic, etc. Nitric, chloric, perchloric, and sulfuric all behave in the same way, but we have our normal arrow here, normal meaning the left to right arrows, not a equilibrium arrow, because these, being strong, go to completion, right? So we have that arrow indicated. So what that means is that if we have a strong acid, we can actually predict, just based on the stoichiometry, how much of the hydronium ion we actually have, right? But we need to know whether it's a strong acid in the first place. So down here it says calculate the pH of an aqueous solution at 25 degrees that is 0.035 molar in HI, right? So let's take a look at that one first. So we have concentration of HI in 0.035 molar. Well, it's HI a strong acid? That's the first question we're going to ask. Strong or weak? If the acid doesn't belong to this list, then you can consider it being weak. HI, hydroiodic, is a strong acid. Okay, and the way that this is going to be helpful to us here is that when HI it dissociates in water, it's going to dissociate completely to give me only H plus and I minus, right? That's what it's made up of. Well, guess what? Everything is in a 1-to-1 mole ratio. At one H plus and one I minus. So if I start off with 0.035 molar of the HI, this should break up to give me 0.035 molar of the H plus and 0.035 molar of the I minus. So the concentration of the species that I'm concerned with now, the H plus or the H3O plus, right, depending on your point of view, I know what that concentration is. So it's 0.035 molar. If I know what that is, I can then do my pH equation. My pH is a negative log of H plus, so that's negative log of 0.035, right? You'll need your calculator, unless you can do logs in your brain. More power to you if you can do that. I would just rely on my calculator, and that's going to give me a pH of 1.46. So when you do these calculations, right, think about the answer that you get. We're starting off with HI, which is hydroiodic acid. So right away, we know that when you calculate the pH, it should be less than 7, right? And that's a quick way just to double check at the end, does the answer make sense or not? And obviously here, being less than 7, it does make sense. So for these strong acids, we can quickly determine the concentration of the species in question, which is the proton or the hydronium, simply by looking at the concentration of the acid in the first place, because it is going to dissociate completely. All right, so very similar to the strong acids, the strong bases tend to be fewer than when compared to all the bases that are there. So the vast majority of bases, just like acids, tend to be weak. So the strong bases are few, but we need to know these, and the way that we can remember them is that they usually consist of the group 1A, so that's a group 1A metal, hydroxide. So lithium hydroxide, sodium hydroxide, potassium, rubidium, cesium hydroxide, and also the group 2A hydroxides, the group 2A elements that are further down in that group. So the heavier of the alkaline earth metals, right? So things like calcium hydroxide, strontium hydroxide, barium hydroxide. If you look in the periodic table, you'll see these are all closer to the bottom of that group. They're the heaviest. So these are the ones that are the strong bases, and just like the strong acids, they will dissociate completely in aqueous solution. Okay, and if they do that, we're going to see the same type of full-headed arrow. It's not in equilibrium. Okay, we're going to assume that these will go to completion. We're not equilibrium systems, which means that predicting the hydroxide concentrations and calculating pHs, etc., tends to be a much simpler example or much simpler scenario. So let's take a look at an example specifically now of this one. So it says calculate the pOH of the following, and we'll pick on B here. All right, so we're told that we have a concentration of the barium hydroxide is 0.013 molar. Okay, just like with the acid, we need to look at that thing. First of all, we need to know that it's a base. Right, and that means when you calculate the pH, right, the pH should be greater than 7. That's before doing anything, we know exactly what range our pH should be in. So it's a base, yes. Is it strong or is it weak? That's the second question. Right, and it belongs to the group 2A metal hydroxide, so it's a strong base. So that's going to break apart then. We write the equations for this. When this dissociates, we get the barium ion, BH2 plus, and then we get two hydroxides, so two OHs, hydroxide ions. So if I start off with 0.013 molar of the barium hydroxide, again, according to the stoichiometry, right, you get a 1 to 2 ratio. So whatever barium hydroxide I have, I'm also going to get that barium ion concentration being the same. And now for the hydroxide, now it's a 1 to 2 ratio, or twice as much. So it'll be 0.013 times 2, which is now equal to 0.026 molar. Right, so here we're using the stoichiometry of that equation to determine the concentration of the hydroxide. Okay, so once we have the concentration at the species in question, we can now calculate the P with asking for the pOH pairs. The pOH would be the negative log of the hydroxide. Okay, so that would be negative log of 0.026. All right, stick that in your calculator. You end up with a pOH of 1.59. Right, we take this one step further. If you want to find the pH, this would be equal to 14.00 minus 1.59, and that would be 12.41. As a pH, guess what? We should look for that pH to be greater than 7 because we had a base to start with. Okay, so for strong acids, for strong bases, it's easier to calculate pHs or pOHs simply by assuming that these reactions, these dissociation reactions into the hydronium or the hydroxide will go to completion, and we can use the stoichiometry to determine the concentrations of the hydronium or the hydroxide concentrations.